Artificial intelligence, it's a brain so bright. A tool for solving logistics with might. Actions, planning, and logic unite to find solutions in state space with light. As the Matrix tells us with sight, the biggest challenge is making the right choice. But AI shines light in data's dark night, bringing solutions with speed, making life bright. In the search of state space, AI finds its way. From autonomous cars to smart homes, every day. It's changing our world, come what may. It's our future, a friendly light to guide the way.
Not a bad poetic definition, but now let's try to define, as engineers, what artificial intelligence is. At the beginning, we will focus only on most basic terms, define them and explain them by examining specific cases. Before us is a Bible of artificial intelligence. The book is used in practically every university in the world. A 1,000-page book that provides descriptions, methods, and algorithms of both classical and modern artificial intelligence technologies. Let's see how often these basic terms are repeated in this book. When it comes to artificial intelligence, it's important to understand key terms such as state. The state space is a collection of all possible states that the system can have while it's being calculated. It includes the initial stage, which is the state the system is in when it's first turned on, and the final stage, which is the solution of the problem. Actions are functions programmed by the developer that take in specific state and returns all possible actions that can be taken in that state. Transitions are another type of function, also programmed by the developer. They take the current state of the system, and the action is being taken as well, and return the new state that the system will be in after the action is completed. Finally, the state space siege is an algorithm that helps find a path from the initial state to the final state, or the solution to the problem. It's important for students to remember these terms as well. To make these reference terms more concrete, let's look at a specific example, a navigation system. Let's say we are trying to get from Constitution Avenue in Vilnius to Klaipėda city. At the intersection of Constitution and Calvary Street, the navigation system will make decision on which direction to take. For the sake of this example, let's label this intersection as A. The state space in this scenario is all the intersections in Lithuania and their names. At the intersection A, there are 4 possible actions: move north, move south, move west, and move east. The transition function takes the current state, intersection A, and an action, such as move west, and returns the name of the new intersection. Let's call it B. Similarly, if the action is move south, the transition function will return the new state, intersection C. By looking at this example, IT students can better understand the concepts of state, state space, actions, and transition functions in the context of navigation system. The next example we will look at is from the application of artificial intelligence in games. Just a few examples. AlphaGo, a computer program developed by DeepMind that beat the world champion at Go. OpenAI 5, a team of 5 AI agents that defeated professional human teams in popular game Dota 2. Liberatus, an artificial intelligence system developed by Carnegie Mellon University, beat the top 4 professional poker players in 20-day tournament. Therefore, let's see how our 5 terms are reflected in such systems. In front of us is a collab document, the link of which can be found in the description of this video below. Here is an example of program where computer learns by playing a tic-tac-toe game with itself using deep neural network. As I already said, the state of the system is a variable with its specific values. The minimum number of variables needed to fully describe the operation of the system is the art of programming. In our case, we see that the game has 9 cells, and intuition dictates that 9 variables should be enough, where 1 variable is for 1 cell. Next, what is the initial state? Empty states with variables equal to 0. The size of the state space is the amount of such possible combinations, and it's equal to approximately 3 to the power of 9. It should be clearly noted this is an approximate estimate. We do not take into account the fact that crosses and zeros are placed one after each other. Very often in computer science, this is written using big O. The action in this example is the placement of a cross or a knot, which we realize by changing the value of the corresponding variable. The state transition function in this game takes the current version of the game and the player actions and returns the game board with the player's movement already represented. The siege in this game is the examination of such sequences of actions in which the corresponding player wins. In this example, a deep neural network performs such siege while playing with itself. We will come back to this example when we briefly touch one of the technologies of machine learning and deep neural networks. The last example that we will touch on very briefly is an autonomous car in virtual 3D environment. VBots, robot testing virtual environment before us. An autonomous car is relatively simple. It has 4 sensors: camera, laser distance meter, speedometer, and GPS navigator. There are also 2 actuators, a speed regulator and a steering wheel. In this case, the system state is the values of all these device variables. Initial state, when the speed is 0 and the steering wheel is not turned. The state space in real life would be infinite, because quantities such as speed are defined by a set of real numbers. In virtual space, the size of state space is finite, but it can be said that it is very big. The action in this example is the values of the actuators, the value of speed controller, and the angle of rotation of the steering wheel. The state space transition function in the simulator is the whole system called physics engine. The system takes all 3D objects and calculates the new state of these components using the law of physics. The 3D video component renders this on the screen.